Good evening. Hints for homework 5, well, really workshop questions 5. Two homework questions, A1 and A1 and A2. We're now going to look at B1. Find the solution candidates for maximizing f is x squared plus y squared subject to x squared over 9 plus y squared over 25 is less or equal than 1 by forming a suitable Lagrangian and applying the first order conditions. Then apply the Hessians for the relevant Hessians for the solution candidates. So, well, we expect multiple critical points. So we have to see which critical points are for binding. So lambda bigger than 0 or non-binding constraint. So let's write down the Lagrangian. Lxy lambda is fxy minus lambda. What do we have? Let's gxy minus b. Yes, which is x squared plus y squared minus lambda, and those are circles, and this is an ellipse minus 1. So we need the first order conditions. So it's the LDX is 2x plus minus lambda 2x over 9 is 2x 1 minus lambda over 9 is 0. The LDY is 2y minus lambda 2y over 25, so that's 2y. 1 minus lambda over 25 is 0. That's 1. That's 2. Number them. Then we need the CSC, in this case 1. So you have only 1. Inequality constraint. We better say this. We have an f is x squared plus y squared and a g which is x squared over 9 plus y squared over 25 less or equal than 1. So this is x squared over 9 plus y squared over 25 minus 1 is 0. And then we have the inequalities. So what are the inequalities? We know that lambda needs to be bigger or equal than 0. And this one needs to be just the imposed inequality constraint. So from 1 we get what is it? From 1 was 1. X is 0, or lambda is 9. And from 2 we get y is 0 or lambda is 25. So then we have 3 options. 0, 0, x comma 0, and 0 comma y. Call that cases 1, cases 2, case 3. And then in case 2, of course, we have x when x is non-zero, we have lambda is 9, and when y is non-zero, we have lambda is 25. So if we look at 0, 0, then this is 3, this is 4. If we look at 0, 0, then we still have to solve, well, obviously when 0, 0, then we're in the interior, but then for 0, 0, lambda is 0, so not binding, not binding. So then we need to calculate the Hessian. So let's do that. So lambda is 0, case 1, that was 0, 0, not binding. The constraint is in the interior. Constraint is not applied, and we need to calculate the Hessian. H is to classify, so fxx, fxy, fyy, yx, and fyy is, and then use the principal minor test for the critical point 0, 0. Let's go back to the other one. Let's do red. So we need to look at red here. So x0 lambda is 9, so lambda is 9, and then we need to take care that we're on the ellipse. So if we're on the ellipse, then we have to determine x from 3 given y is 0. Then the constraint is binding. Likewise, if we do 0y, lambda is non-zero, so from 3, we determine y, and then we have everything. And it's again not binding, so it's binding, sorry. So cases 2, 3 are binding. Need the bordered Hessian. So, and we need to apply the principal minor test for bordered Hessians. So HB is, this gets a bit more complicated. We need to take the we need to now take the gradient of g, so that's 2x over 9 plus or minus 2x over 25 to y over 25. What am I doing? To y over 25. And like I said, for if you go take the second order derivative of the Lagrangian with respect to x and lambda, so then you get the minus sign here. But if you ignore that, then you get the plus sign, then you get the gradient of h. So, and as long as you're consistent. So in the Lagrangian, we go back to the Lagrangian, which is here. We need to take now the double x derivatives, xx derivatives, the xy derivative, yx, and the yy. So the x derivatives gives us 2 plus 2 lambda over 9. 2 times 1 minus lambda over 9. This gives us 0 because there are no cross derivatives. This is 2. This is lambda, right? Not x. Oh, that's a bit dangerous. This is 9. This is minus 2 lambda over 9. This is 1 minus 2 lambda over 25. So now you need to evaluate HB at the critical points and evaluate whether rule A applies or rule B. And in this case, M is 1 and N is 2. So we are in chapter 3, and here we are in chapter 2. Now in C, you're asked to make a sketch. So we have circles. We have circles as contour. So you take, you draw various circles. But you need to be in the, so x is plus or minus 3. Well, this doesn't fit. This is x is plus or minus 3. Y is 5, so that doesn't fit. So that doesn't fit. So this is a bit too ugly. Trying to write y-axis, x-axis. So this is 3. This is 3. 1, 2, 3, 4, 5. That's 5. 1, 2, 3, 4, 5. That's 5. So we're inside the ellipse. You see, you can do this whole problem geometrically, and then we have the circle. So the first circle goes like this. The largest circle. It's a circle with, oh no, completely wonkers. The largest circle is the circle with radius 5. You need to draw a proper circle, so you see that the maxima must lie here. And this is probably a minimum. And then here you have 0, 0, that I suspect that's a minimum. Maybe this one is a saddle, but these ones are clearly the maxima. So this is y, this is 5, this is 5, this is x. So you can solve the problem basically. Yeah, so these are local minima, and what? Yeah, so these three are local minima, and this obviously is a maximum because it's the largest contour level which is allowable for the solution to lie within the ellipse. So let's go to B2. Scroll further, B2, write down the, let's see, make it a bit larger. B2. So B2, let's see where we are. B2, A, classical Lagrangian, F, subject to 3 inequality constraints. We're in the circle, but x and y are bigger than 0, so we're in the first quadrant. So that's the picture. So you can almost so we are in this quadrant, so within the circle, and then 2y squared minus x. So we could, so x is 2y squared, so 2y squared minus x is c. So you could try, you could do this actually geometrically. You draw various contour levels. Say C is 0, 1, 2. C is 0, 1, 2, and then you can solve it geometrically, which is then not sketch. Yes, that's class in B. So I'm not solving that, but that's what you need to do for B. So you can actually. So for C is 0, you get x is 2y squared. And for C is 1, you get x is 2y squared minus 1. Well, maybe you need C is minus 1, but we'll see. You have to make a couple of sketches. X is 2y squared. What does that become? So when y is 1, when y is 1, x is 2. So that's y is 1, x is 2. And let's do when y is 1 over the square root of 2, x is 1. So x is positive, so must look something like this is there. So x, y is plus or minus 1, yes. Y is plus or minus 1 gives it that, so must look something like this. Let's see is 0. Yeah, C is 1. So C is 1. C is 1 gives us what's problem is it's minus 1. C is 1. X is minus 1. X is minus 1. So y is 0. Y is wait a minute. Y is 0. X is minus 1. And we here. Y is 0 gives us x is minus 1. Y, x is 0 gives us, what is it? X is 0 gives us, y is 0 gives us x is 1. Y is 1. Y is 1. Y is 1 gives us x is 1. That's y is 1 gives us x is 1. Y is 1 minus 1 gives us x is 1. C is 2 gives us x is 2, y squared minus 2. So then we start here. So x is minus 2 for y is 0. Y is oh, it's too high. So they seem to be going this way. So larger. So there must be 12. Let's see, is that right? Y is 0 gives x is minus 2. Y is 1. That's what I want. Y is 1 gives us x is 0. So then we're here. Is it that tight? I'm not surprised about that. Well, then you already see that C is 2 gives you the maximum for F, because this is C is 2. So basically we have already geometrically solved it. But we're asked to write down the Lagrangian, 5 inequalities, 5 equalities, 6 inequalities. Ooh, that's a lot. Yes, so we need the Lagrangian, x, y, and now lambda 1, lambda 2, lambda 3, which is the function itself, 2y squared minus x, minus lambda 1 for, what is it, the circle, minus lambda 2. So this is plus lambda 2x plus lambda 3y, because it's minus lambda 2 times minus x, because minus x, yeah, you have to be careful, minus x is less or equal than 0, minus y is less or equal than 0, which means x bigger than 0, y bigger than 0, which is what we have. So that's the Lagrangian. B, f of c's and the c of c's. So the f of c is Lx is 0, the y is 0. Let me write write that differently. So it's 0, so you have to write that out. And then, of course, you have the 3 CSCs, lambda 1 times this constraint is 0, so the CSCs, so lambda 2 times just x is 0, and lambda 3 times y is 0. Yes, and then the inequalities. What is it? The inequalities themselves, less or equal than 1, x bigger than 0, bigger or equal to 0, y bigger or equal than 0, but then lambda bigger than 0, lambda 1 bigger than 0, 2 bigger than 0, lambda 3 bigger than 0. And you need to solve then all those. Yeah. So it's important in this case, what you can use is that lambda 2 and lambda 3 need to be bigger than, lambda 2 needs to be bigger than equal than 0 and lambda 3, and that you can use, oh, what is this now? Sorry, I don't know what happened there. Yeah, I do. They want a software update in the middle of making a movie. So important here is that lambda 2 is bigger than equal than 0. Let me write down the LX1. So the LX1 is, let me do the previous one. Let me write down the LX and then you do the LY. So LX is minus 1 minus 2 lambda 1 x plus lambda 2 is 0, and that's 1. This becomes 2, this becomes 3, this becomes 4, this becomes 5, this becomes, well, I grouped them together, it's 5, 5, and this is 6. So minus 1 minus 2 lambda x minus 2 lambda 1 x plus lambda 2. Let's look at that one. So that's minus 1 minus 2 lambda 1 x minus lambda 2 is 0. So that means that plus lambda 2, because it's plus. So yeah, I had plus that, yeah, plus lambda 2. So that means that lambda 2 is 1 plus 2 lambda 1 x, and lambda 2 needed to be bigger than equal than 0 because of 6. But 1 is bigger than 0. Lambda 1 squared is also bigger than 0. So that must mean that x is bigger than so lambda 2 needs to be bigger than 0. So lambda 1 needs to be bigger than 0. And we also had, not forget, x bigger than 0. And we had x bigger or equal than 0. And since we had, and this is what we later we use in Kuhn-Tucker theory, is we had lambda 1 times, we had from 5, lambda 2 of x is 0. That was one of the CSCs. That was number 4. but lambda 2 is bigger than 0. Lambda, no, it's even worse. What I'm saying, lambda 2 is bigger than 0, because lambda 1 is bigger than equal than 0, x is bigger equal than 0, and so this is always positive, non-negative. That means, given the 1 there, lambda 2 is bigger than 0. But when lambda 2 is bigger than 0, that means the constraint is binding and x is 0. And you can now reason from there. So now you need to get the other one. So that comes out of the 1 for 1. So I'll let you figure out. So now you need to use this one to get the you also still need to solve that one. So you need to that one gives you that y is 0 or lambda 3 is 0, and you need to split that up. So continue with lambda 3 times y is 0, which splits in lambda 3 is 0, or y is 0, which you need to consider in separation with the fact that you already know that x is 0. So you get two critical points, and so in this case, at least with lambda 2 bigger than 0, that's a binding one. So for x is 0. And then you need to, so in C we need to, so in case C you can't do yet because it's from the lecture next Wednesday, but in the Kuhn-Tucker theory, basically you take care of the positivity constraints first in an updated theory, and then you derive a Kuhn-Tucker Lagrangian, which only involves the function itself minus lambda, only is one lambda, or lambda 1 if you wish, and then the what do we no, I'm doing it wrong, 2y squared minus x, and then here the constraint, the constraint which is not just positivity of the variables, but that's for the Wednesday class, which Laura is going to teach. And then you can do C. So I'll leave it at that and leave for you to figure it out further. Thank you very much. Have a nice Sunday evening.